In this chapter, we focus on the peak energy consumption and load shifting problem. The practical objective is to reduce electricity cost and reduce maximum peak demand while keeping a logistics hub operating smoothly. We combine two strategies. Peak shaving reduces consumption during expensive high-demand periods. Load shifting moves flexible activities into cheaper off-peak windows. This slide defines the scenario scale and the tariff logic. The hub spans 500 hectares and processes 15,000 20-foot equivalent units per day, using 24 automated cranes and 200,000 square meters of climate-controlled warehousing. Peak demand occurs during day shift from 6 in the morning to 6 in the evening, reaching up to 25 megawatts. Night demand drops to roughly 8 megawatts. Pricing is 15 cents per kilowatt hour during peak and 8 cents off-peak, plus a demand charge of $18 per kilowatt on the monthly peak. Annual electricity costs exceed $35 million, so the target is a 20 to 30% reduction. This slide previews the tier structure. We start with a mixed integer programming model for scheduling flexible loads and operating storage. We then apply a grasp heuristic, a Moth-Flame optimization metaheuristic, and a deep reinforcement learning approach using a deep queue network. Finally, we expand to a digital twin, an autonomous multi-agent ecosystem, and an ethical value-aligned framework. Tier 1 gives us a clean baseline, a mixed integer model that schedules shiftable operations and controls energy storage over a 24-hour day. The model is designed to do two things at once. First, it pushes energy use into cheaper off-peak periods, so the time of use bill drops. Second, it limits the maximum demand level because the monthly demand charge is tied to the single highest peak. The model organizes decisions on three axes. The first axis is time, modeled as 24 hourly periods across a day. The second axis is the set of shiftable operations, meaning tasks you can move in time without breaking service. The third axis is the set of storage systems, such as batteries. Storage is what enables peak shaving. You can charge when prices are low and discharge when the system is under peak stress. The parameters describe what flexibility you really have. Each operation has a duration and an energy requirement, and it also has availability windows that restrict when it can run. On the energy side, you have an hourly price that is higher in the day shift and lower overnight, plus a base demand that you cannot shift. For storage, you need capacity, charge, and discharge rate limits, and efficiency, because you never get 100% of the energy back. The core scheduling decision is a start time choice. For each operation, you pick exactly 1 hour as its start. Storage decisions are continuous. How much energy to charge into storage and how much to discharge out, hour by hour. Finally, the model tracks power demand each hour and also tracks the maximum demand across the day. That maximum is what drives the demand charge, so the model cannot ignore it. The objective has two parts. One part is the energy bill. For each hour, you pay the price times the demand in that hour. The second part is the demand charge term, a penalty applied to the maximum demand observed across all hours. Operationally, this forces the model to trade off cost savings against aggressive peak reduction. The constraints enforce physical and operational realism. Every shiftable operation must be scheduled exactly once, and it must start only inside its allowed time window. Power balance ties everything together. Hourly demand equals base demand plus the running operations plus storage charging minus storage discharging. Storage constraints then enforce rate limits, state of charge tracking over time, and capacity bounds. This figure is the story in one picture. Before optimization, demand climbs during the day shift and hits a peak around the busiest handling window. After optimization, some flexible work is moved into off-peak hours and storage discharge is used to shave the remaining peak. The result should look like a flatter day profile and a higher but controlled overnight load. The slide walks through a compact example over 6 hours with 3 shiftable operations and 1 storage system. The operations are a container crane task, taking 4 hours and 200 kilowatt hours, warehouse heating and cooling taking 2 hours and 150 kilowatt hours, and electric vehicle charging taking 3 hours and 180 kilowatt hours. Storage has 100 kilowatt hours of capacity, a charge and discharge rate of 50 kilowatts, and 90% efficiency. With peak pricing at 15 cents per kilowatt hour in hours 1 to 3, and off-peak pricing at 8 cents in hours 4 to 6, the solution starts the operations at hours 4, 5, and 6, charges storage in hours 4 to 6, and discharges in hours 1 to 3. The reported cost drops from $47,250 to $31,680, a 33% reduction, and peak demand falls from 25 megawatts to 19 megawatts. Tier 2 uses a greedy randomized adaptive search procedure. The idea is to build a feasible schedule quickly using a greedy rule, but to inject controlled randomness so you do not get trapped in the same myopic pattern every time. Then a local search phase tweaks the schedule by moving operations between time slots, keeping feasibility until cost and peak stop improving. Read this flowchart as two loops. The outer loop repeats multiple iterations, each time constructing a schedule and then improving it. The inner logic is the practical workflow. Generate a short list of good start time choices, pick one with some randomness, and update the remaining options. The key benefit is speed. You can get strong schedules without solving the full mixed integer model, which is helpful when the operation list is large or when schedules must be refreshed frequently. This code section typically defines the inputs and scoring logic, operation durations, energy requirements, and allowed windows, plus the price profile and baseline demand. You should also see how the construction phase forms a restricted candidate list. It does not consider every possible move equally. It prefers time slots that are cheap and that avoid pushing demand above a peak threshold. This part usually implements the greedy randomized selection. Instead of always taking the single best candidate, the code samples among the best few candidates. That small randomness is what allows multiple runs to explore different schedules. It is also why Grasp can improve with more iterations. Each iteration is a new attempt, not a repeat. This portion typically defines the local search neighborhood. A common neighborhood move is to shift one operation earlier or later within its feasibility window, or swap two operations. Each move is evaluated by its impact on two metrics: total energy cost and maximum demand. Feasibility checks ensure you never schedule an operation outside its allowed window. Here you typically see iteration management and reporting. Run the construct and improve cycle many times, record the best cost, and track peak reduction. In operations, this is what makes the heuristic usable. You can set a hard time budget, for example, a few seconds, and the best found schedule at the deadline is what you deploy. This slide gives a concrete convergence trace. In the reported run with 15 shiftable operations over a full day, the best cost improves from $45,230 at iteration 1 to $38,940 at iteration 10 to $32,150 at iteration 25 and to $29,680 by iteration 50. The example schedule starts energy-intensive tasks in off-peak windows, such as container loading starting at hour 20, heating and cooling adjustment starting at hour 22, and electric vehicle fleet charging starting at hour 24. The reported result is 34.4% savings and an 8.2 megawatt peak load reduction, which is about 32.8%. Tier 3 uses Moth-Flame optimization, which is designed for complex landscapes where there are many local optima. Here, each moth represents a candidate schedule, and each flame represents one of the best schedules found so far. The algorithm updates moths by moving them along a spiral path toward flames, which is a way of mixing exploitation of good schedules with exploration of new ones. Use this visualization to interpret how the search progresses. Early in the run, moth schedules are spread out, meaning the algorithm is exploring many timing patterns. As iterations advance, the population concentrates around a smaller set of strong schedules that balance off-peak shifting with aggressive peak shaving. This slide shows the spiral update rule that drives Moth-Flame optimization. In spoken terms, each moth updates its schedule by moving toward a chosen flame, but it does so with a spiral-shaped step that includes randomness. That structure prevents the search from collapsing too early. It keeps some diversity so the algorithm can still discover different schedules that reduce peak in a different way. This code section typically defines how a schedule is encoded and how fitness is computed. Fitness here is a cost plus peak measure. It rewards low energy cost and penalizes high maximum demand. Feasibility is enforced by design, for example, by generating start times only inside valid windows, and by repairing any candidate schedule that violates an operational constraint. This portion usually initializes the population of moths and the initial set of flames. A practical trick is to seed some moths from a heuristic schedule, not only from random schedules. That seeding gives the meta-heuristic a strong starting point, while still leaving enough randomness to explore alternatives. Here you typically see the moth update step, selecting which flame to follow and then applying the spiral movement to update the schedule. In energy terms, think of it as nudging operation start times toward patterns that have already shown lower cost and lower peak, while allowing some controlled deviation. This part usually handles flame updates and stopping logic. Flames are updated whenever the algorithm finds a better schedule. Stopping can be a fixed iteration limit or a lack of improvement over time. In operations, you choose this based on how much compute you can afford. This example quantifies the gain. With a population of 50 moths and 1,000 iterations, the reported best fitness improves from $52,340 at generation 0 to $38,920 at generation 100, to $31,450 at generation 300, to $28,150 at generation 600, and to $27,320 at generation 1000. The reported baseline cost is $48,200, so the savings are $20,880, or 43.3%. Peak demand is reduced by 11.8 megawatts, about 47.2%. The run reports convergence near iteration 847 while maintaining diversity above 0.15, and the best schedules place the highest energy operations into overnight windows, such as hours 22 to 2. Tier 4 reframes the problem as a sequential decision process. Instead of creating a full-day schedule once, an agent makes hour-by-hour decisions based on what it observes: current demand, current prices, storage state, and what tasks remain. This matters because real hubs face volatility. Prices, weather, and equipment availability change, and reinforcement learning is meant to adapt to that changing context. This architecture figure shows the deep queue network setup. The network takes a compact state representation and outputs action values, meaning the expected long-run benefit of different scheduling and storage actions. The key components are experience replay and a target network. These stabilize learning so the agent does not overreact to a single unusual day. The reward is designed to encode business logic. It penalizes energy cost in the current hour, adds an additional penalty when demand approaches a peak, and can include an efficiency bonus for meeting service targets with less energy. In the model described here, the reward weights are treated as adjustable, so the system can shift behavior depending on whether cost reduction or peak reduction is the priority. This code section typically defines the environment, how demand is computed, how storage state evolves, what it means to start an operation, and which actions are feasible. A key practical point is action validity. The environment must prevent the agent from choosing actions that violate operation windows, exceed storage limits, or break safety constraints. This part usually defines the deep queue network model and the action selection policy. The policy is often epsilon greedy, meaning it explores early and becomes more selective as training progresses. The network inputs include signals like current hour, demand level, a price forecast window, operation completion flags, and storage state of charge. Here you typically see experience replay. The agent stores transitions of state, action, reward, and next state, and then learns from random mini-batches. This breaks correlation in the training data, which is critical when the environment is driven by daily cycles and repeated patterns. This portion generally covers the target network update and the loss computation. The target network is updated more slowly than the main network to stabilize the learning target. Operationally, this is how you avoid chaotic behavior, where the agent constantly changes its policy and never settles into a reliable scheduling strategy. This final code segment usually ties training together: episode loops, epsilon decay, logging, and evaluation. For a production setting, This is also where you would add safeguards, such as constraints that cap peak demand even if the agent explores aggressively. This example reports training over 2,000 episodes. The average score improves from about minus 2,150.5 at episode 0 to about minus 1,680.2 at episode 100 and to about minus 875.4 by episode 1,000, while exploration drops toward 1%. The reported baseline using a random policy is about minus 2,200 average reward, while the trained agent reaches about minus 650, which is a 70.5% improvement. This slide illustrates why learning-based control is attractive. Under normal operations, the reported cost is $28,400 compared with $45,200 baseline. Under stress events, the agent still adapts. During a peak demand event, the cost is $31,200, compared with $58,900, and during a grid instability event, the cost is $29,800, compared with $52,100. The learned behaviors include preemptive storage charging before predicted peaks, postponing flexible operations during price spikes, and coordinating load balancing across subsystems. Tier 5 introduces a system of systems digital twin. The purpose is to simulate energy, operations, and constraints together, so you can test strategies safely before you apply them. The digital twin links electrical dynamics, thermal behavior in warehouses, equipment efficiency and degradation, weather, and operational workflows. That integration is what reveals second-order effects, like how rescheduling crane work affects yard flow and downstream charging needs. The architecture is layered. At the bottom are physical assets and sensors. Above that are communication and data processing layers that turn raw signals into a clean operational state. On top of that sits the digital model layer, combining physics-based simulation and predictive models, and finally an application layer that runs optimization and decision support. The key is that decisions are driven by a consistent, validated digital state. This slide reports system-level metrics. In the baseline scenario, daily energy consumption is 450 megawatt hours. Peak demand is 25.2 megawatts around 2 in the afternoon. Daily cost is $52,100, and system efficiency is 78.3%. With digital twin recommendations, daily energy drops slightly to 445 megawatt hours. Peak demand falls to 19.8 megawatts. Daily cost drops to $38,900, and efficiency rises to 84.7%. Tier 6 moves beyond a single optimizer into a distributed ecosystem. Each major energy actor becomes an agent. Cranes, heating and cooling zones, electric vehicle chargers, storage units, and grid interfaces. Agents negotiate and coordinate in real time. This makes the system faster to respond and often more resilient, because a local failure does not have to wait for a central controller to replan everything. This architecture is a network of specialized agents. Producer agents represent storage and on-site generation, consumer agents represent equipment and buildings, coordinator agents manage load balancing, and market agents represent tariffs and demand response opportunities. The key design point is shared negotiation protocols, so agents can trade off cost, timing, and reliability without violating operational constraints. This slide gives concrete emergent behaviors. In one event, when a transformer fault occurs, the system redistributes about 8.2 megawatts within 12 seconds and maintains 98.7% operational capacity. In another behavior, storage agents form a consortium around a predicted price spike, pooling 45 megawatt hours and earning $12,400 in arbitrage revenue while maintaining reserve. It is also reported that crane agents learn coordinated sequencing that reduces energy consumption by 18.3%. This comparison focuses on speed and resilience. Over a 30-day analysis, the centralized system averages $38,900 per day, while autonomous agents average $31,200. Peak reduction improves from 21.4% to 28.7%, and response time improves from minutes to seconds. In short, distribution trades some central simplicity for stronger real-time adaptation. Tier 8 adds non-negotiable guardrails. Peak reduction cannot come by shifting harm onto vulnerable communities or by pushing workers into unsafe operating patterns. In this framework, ethical boundaries are treated as constraints first, and optimization is allowed only inside those boundaries. This architecture is described as a hierarchy. Constitutional constraints sit at the top as hard rules. Below them are policy constraints like compliance and corporate responsibility, then stakeholder constraints like community welfare, and finally traditional performance constraints. The operational implication is that the system must explain its choices and prove it did not violate protected priorities. This example tests the framework under stress. In a severe heat wave, the grid requires a 15 megawatt demand reduction. A profit-only approach might curtail community-critical services. The value-aligned strategy protects healthcare and elderly care facilities, and instead delivers reductions from industrial and flexible loads. 8 megawatts from crane operations by rescheduling to night shift, 2.5 megawatts from non-essential lighting, 3 megawatts by delaying non-emergency electric vehicle charging, and 1.5 megawatts from administrative building heating and cooling adjustments. The reported cost increase is 12.4%, about $4,800, but critical services remain fully protected. This slide summarizes longer-run outcomes. Reported carbon emissions run 18.3% below the regulatory requirement, and renewable energy utilization reaches 67% compared with a 45% industry average. On equity and workforce outcomes, the reported energy cost burden on low-income areas is reduced by 8.7%. Worker safety remains high, and the system provides explanations for all major decisions with regular oversight meetings. Use these questions to test whether you can translate the story into a decision model. For Tier 1, you are asked to schedule 5 shiftable operations under a 2-tier tariff, and then extend the model to include storage and demand charges. The goal is implementation readiness. You should be able to define variables, write constraints in plain English, and compute the schedule implications for both cost and peak. To close, peak shaving and load shifting reduce both time of use energy cost and demand charges tied to monthly peak demand. Exact optimization provides a feasibility baseline, heuristics and metaheuristic scale search, and reinforcement learning enables real-time adaptation. Digital twins and multi-agent systems capture resilience and interdependencies, while value alignment keeps decisions safe, fair, and sustainable.